At that point in time, water adds, eventually form a carbon and one oxygen here, and you end up with a ketone. So this was one of the, in chapter 18, one of the strategies to get ketones, to add a Grignard to a nitrile.
Can you do A for 3 too?
On that same one?
Yeah, the same one.
So, alcohol is an awful living group. So if we're going to do an SN2 reaction, we need to convert it into a better living group. One possibility would be to convert it into a halide. But another possibility is put tosyl chloride. This attacks the tosyl, eventually will get rid of the hydrogen, and you form this tosylate. Tosylates are very good leaving groups because there's all of this resonance stabilization of the tosylate group that leaves. So this is just like having a bromide there. You just have a really good leaving group. So the thing in here says, okay, let's first put the tosyl chloride to form the tosylate, and then we put sodium cyanide. So the cyanide ion comes, displaces, just like it would do with a halide, SN2 reaction, and we're going to have this. Right? So that would be the first product that I wanted. And then we hydrolyze. So nitriles, if you hydrolyze mildly, will give you an amide, but if you heat it with sulfuric acid, you're going to go all the way to the carboxylic acid. So this then, we have these two carbons, and then of course now we have this other carbon, which will become a carboxylic acid. How could I have done the same thing from here?
Grignard attacking CO2.
Make the Grignard, add CO2, hydrolyzed, and that will get you that same product. Right? Because you're adding one carbon from the carbon dioxide, and that would get you that same product. But the strategy is the same. We know that both nitriles and halides can be converted. Our strategy is to add one extra carbon. The nitrile is the extra carbon, or the CO2 is the extra carbon once you form the
On 3D.
3D, okay. So the first step is this first step. So you have an alcohol, put PBr3, make the halide. Now, this is a vivid reaction. So, in the first two steps, you triphenylphosphine and N-butyllithium on the halide form the ylide, right? So, your triphenylphosphine comes in, you get that, then you put a base, your N-butyllithium, which extracts this hydrogen and forms this ylide. The ylide will then add to the carbonyl in that aldehyde and benzaldehyde. So when you put that ylide in the presence of benzaldehyde, initially this is going to add, you're going to form an alcohol, but then an alkoxide ion, but then these two will react and leave. So basically what we have is we're going to end up forming a bond right here between this carbon and this carbon, which is then connected to this. Initially, we have the triphenylphosphine and the oxygen, but that leaves and forms a double bond here. So that is your Weyl reaction. So for C, we formed, okay, so this is B, and 3C. So we're starting with an acid chloride. If we just put lithium aluminum hydride, we're going to add twice and go to the alcohol. So what we do is we add a bulky hydride at low temperature, and that's going to stop at the aldehyde, right? Then we're going to add a secondary amine. Remember, your primary amines condense with a carbonyl to form an imine. Your secondary amines condense with carbonyl to form enamines. So, when this secondary amine condenses with this aldehyde, we're going to form an enamine. So this piece is coming from here, and then this is going to add here and form an enamine. Yes.
So you do 4D?
4D. Also on the A form?
Yeah.
So we're trying to make this, and
So it's sorry, 4D.
oh, for D,
Yes.
I'm sorry. Okay, so this is again acidic. So the base here is just so that you equilibrate between the ketone enol form. So just like we did in here, where we formed this double bond and this piece was coming from somewhere, and then this piece was coming from somewhere else. I'm sorry. This is an aldol condensation, it's not a acidic. So your aldol occurs when you have some sort of ketone or aldehyde in equilibrium with the enol, right? And that equilibrium you make under a sort of basic hydroxide methoxide condition. So you have about an equal concentration of the two. Your nucleophile is going to attack your electrophile. you're going to form this, and then this is going to add here. Eventually, when you put this in water, you're going to pick up this, and depending on how acidic and how much I hydrolyze this, you may eventually get rid of the water here and form a double bond between these two. So the idea is, whenever you see an alpha beta unsaturated ketone or aldehyde, or an alpha, a beta hydroxy aldehyde ketone, you think aldol condensation. And your double bond is going to define which piece is coming from where. And the one with the carbonyl is exactly the molecule that you started from. So the blue piece here is what you started off in here. So when we look at this, we look at this piece that connected to this piece. This is the original aldehyde that formed the enol and added to itself. And of course what happened here is I oxidized an alcohol to the aldehyde.
Can you do 7A on test A?
7A. So you're starting from this, and you're going to end up with this. So as usual, we figure out what comes from where. So this is coming from here, and clearly I'm going to need a source of truth, and I'm going to need to make this bond. So I'm making a carbon-carbon bond. Some of the techniques you may think about as Grignards, or some carbon-carbon bond forming thing. Also, the fact that this is an alkane, so clearly I'm going to need to get rid of oxygen. And getting rid of oxygen, one of the ways is reducing via Clemmensen reduction, Vogt-Kishner, stuff like that. So first of all, it would be useful to at least from here make this. Because then I could easily reduce this to the other thing. So it's a question of how do we make ketones. Well, we looked at things like nitrile, adding a Grignard, you can form a ketone. But another very useful technique directly from a carboxylic acid is by using an organoleptic. Because if you put two equivalents of, three carbons. Of this organolithium, the first one acting as a base and removing this, forming the lithium salt, the second adding as a nucleophile and adding here, and then you toss the whole thing in water, you get directly the ketone. That was one of the strategies that we learned to make ketone. And then from that point on, it's just, let's reduce it. Let's say we use Clemmensen reduction or Vogt-Kishner, and that will get you that bond. It is rare that I will give you one of these sentences that's gonna be 5, 6 steps. Usually, in a couple of steps, you can get yourself there. I don't mind 5 or 6 steps, but they need to be somewhat logical. Okay, so this was 2, no, 1, we've done 1. And the question was, why would this not be the major product? So the idea to get this product would be for this nucleophile to come and attack here, hydrolyze, and I would just do that. But what's the problem? You have a strong base, as well as a nucleophile, and you have an acidic hydrogen. So, given a competition between an acid-base reaction and a nucleophile addition to something that's in the middle of the molecule, trust me, the acid-base is going to win. This is going to attack this, form this alkynyl anion, and when I toss this in acid, we're going to pick this up again and give me back my starting material. So we're never going to get to form this. So that is why with Grignards you have limitations, and I kept putting one of the problems, I forget the exact thing, but in this last exam, at some point in time, you guys were trying to make something, and you would get to something like this, and then you said, oh, I'll put magnesium and CO2 and whatever, and form that. What's wrong with that picture? We have an acidic hydrogen. You cannot make Grignards with acidic hydrogens around and expect that not to attack something else. So that is not viable. What would be viable in here would be to somehow start from this and then hydrolyze this to that. But that would not work.
Anybody else missing their exam?
Anything else?
On exam 3B, number 2.
Oh, the negative.
Yeah.
Ah, okay. So, I'm not going to ask you to do a mechanism of it, but if you are under acidic conditions, you cannot have negative charges at any point in time, because they're just going to react with the acid. If you're under basic conditions, or something, you cannot have positive charges. Because it will react. So right off the bat, do not start writing on oxide ions or something like that. That's ludicrous. Okay. Second, when I put acid in a mechanism, this activates things. Like, for example, make a poor leaving group into a better one, or make a poor electrophile into a better one. Right? That is typically why you have acid. So, if you had a carbonyl, which is a decent electrophile, but if this attacks H+, now this is a much better electrophile. You could write this resonance structure and put a positive charge on the carbon. Clearly that's a better electrophile. So that would be an example of 2. An example of 1 would be if I had an alcohol and this attacks H+. This is clearly a much better leaving group than OH-, right? So these are the type of things that you're looking when I put something with H+. Let's use it to activate, to make a better electrophile, to make a better leaving group. And you start there. That's your first step. So when you have this, and you're trying to make this, you're clearly trying to add this heat, which means I would like to make this into a better electrophile, which means your very first step is going to be, let's make this into a better electrophile by reacting this with H+ and forming this. Why do I need a better electrophile? Because, this is not the strongest nucleophile in the world. It's not an alkoxide ion, which you should not write because that under acidic conditions. It's a weak nucleophile, so I want a better electrophile, so it can then attack it. So this will attack. We form an OH. This hydrogen is still attached here, so let's do something with it. Once you form something with a positive charge or a negative charge or a reactant intermediate, do something with it. You cannot carry this through for the next 5 steps. So, some base, anything, another, molecule, glycol or whatever, is going to come. Let's put this as solvent and abstract this. I need, in my next step, for this to attack here and for this to leave. But this is a lousy leaving. So how do we get this to leave? You make it into a better leaving group. How do we make this into a better leaving group? by attacking H plus. So we're gonna have this attack H plus here. I could have written this in 2 different steps, but I'm trying to save some space here for rewriting. So now I would have this better leaving group, this like this, which can now attack because this is going to leave. And now you have, you're almost there, except of course we need some solvent coming in, abstracting this hydrogen, and now I have the product. But this is this acid pushing and pushing, right? We added it here, we added it here, and here to make a better electrophile, and here to make a better leaving group. That is your catalyst that drives this reaction forward, and without which you would not get any reaction happening. Anything else? Okay, so from that to a Diels-Solvay reaction. Okay, so there's your diene is your nucleophile, your dienophile is your electrophile. So first of all, how do they add? Okay, we need your negative end to add to your positive end. The negative end in here is this one, right? I could write some sort of resonance structure here that puts negative charge here. So this negative end is going to add to the more positive one. In here, I'm not going to write resonance structures, but clearly the fluorines are very electronegative, so inductively they are withdrawing electron density from this end. So I'm going to put my positive end on this side, so the negative adds to the positive. Now, that is as far as your regiochemistry. We add like this or like this. Now comes the stereochemistry, which is, and we know that typically any substituents, because they kind of form temporary interactions with your double bonds, tend to end up at the low. Kind of the substituent leads the way to interact with the double bond, to the pi electrons. So the end of rule would tell you that when you form, so let me go back to how we usually get that figure. So when you form your cyclohexene, this, right, this is the new bonds that is formed, and this is going to be underneath, and of course this hydrogen is going to be up, and this is gonna be down. We said that in cyclovision, you can have 1, 2, or 1, 4 are okay, but you're never gonna have a 1, 3 cyclovision. So if you had started from this, you would have ended up with something like that, and you should immediately recognize that that's not an option, because it's a 1, 3 cycle.
I have another question. Okay, you found A, C, and B on exam 3. I 3A.
3A, which one?
We got number 3, A, C, and B.
So we did A, we did C, and we did D. Well, I'll put these notes on D2.
Thanks. Thank you.
For exam 3B, number 3.
Oh,
Yeah, with the one with the 2 equivalent of CH308.
so this was the cyclohexanone,
Yeah.
cyclopentanone, and which one?
The one that says 2 equivalents of CH308. H3.
Oh, that's a protection, right? So we've done this, and that gives you this. Rather than having the two OHs together, we have them separate. So let's say OH CH3 and OH CH3. So rather than being these two connected together, you're just going to have like that, right? You either have two OHs or two OHs. They could be together or separate, but this is a way of protecting a ketone in the acetate or ketone.
And the one with LBA.
So lithium diisopropylamine is a very strong base. So this is one of those reactions that we studied in the little bit of chapter 22 that we covered, which is a very strong base will come and extract this hydrogen alpha to the ketone. Very strong base meaning we're going to form 100% of this anion, which then can go ahead and attack a variety of things. And in this case, it's an SN2 reaction on an alkyl halide. And we just end up adding another group. We don't put like methoxide ion because then we would get an alkyl condensation because we have equal concentrations of ketone and the enol. But with a strong base, and then we have 100% of the anion. Okay, so. So we are going to make this. And the question is, in which order do we add the substituents? So we need to consider, first of all, these two are ortho. These two are para. And these two are meta. So we need to introduce them in the right place. Also, this is the activating. Which probably means we want to introduce it last because a whole bunch of reactions will become difficult with this present. Now this is the activating again as well. So this is a meta director and deactivating. This is an ortho para director and deactivating. And this is a meta director and deactivating. So I could potentially introduce a chlorine and then put this ortho here, but I'm not going to be able to put the nitrogen group as is. And everything is deactivating, so it's also going to be difficult. So I need at least one orthopara director here so that I put things where I want. And if I had a methyl group here as an alkyl group here, then that would be an orthopara director. It would be activating. I could introduce this, and then I could oxidize this to the carboxylic acid. So that's something that we really need to keep in mind. I forget that I told you that you can start from. Oh, so you're starting from toluene. So I'm already telling you, be smart and start from toluene. But don't first convert it to the carboxylic acid because you're losing what you need. I need something that is going to guide this in here and guide this in here. Preferably the nitrogen group last because that's the most deactivating. So let's first introduce the chlorine ortho. This is an orthopara director. So introduce the chlorine ortho. I'm of course also going to get some para, but I cannot avoid that. So somehow I'm going to separate these and just leave it to the ortho. And then I need to introduce something here. Now, since this is deactivating and this is activating, it's going to be the methyl group that is going to guide that second group para. So I'm still leaving this as is and just introducing this para by putting some nitric and sulfuric acid. And now I can go ahead and oxidize. There's no problem with oxidizing because everything else is as oxidized as it could possibly be. So let's just oxidize, let's say with potassium permanganate, sodium chromate, or whatever, and hydrolyze at the end of the day, and that will get me the product that I want. So it's a question of understanding directing groups and the autoparameter and activating and deactivating. Don't put your most deactivating group first, then you're not going to be able to do anything.
Can you go back to exam 3, problem 1 with the NaOCH2CH3, where it reacts with itself?
Oh, yeah, so again, we have an aldol condensation. So I have this, and I put sodium methoxide, and I say react with itself. So under sodium methoxide conditions, we have these two present simultaneously, my nucleophile attacking my electrophile. Initially, I would have this product, which I would accept, or if it dehydrates, then I would end up with this product. Right? But that would be again an aldol condensation.
Thank you.
I know we have a final before us. I'll try to get here a few minutes early if there's nobody in class to get that early. So send the student or whatever who can be here. And if there's something afterwards, I don't mind staying later. We might chase it.
Around the exam, that's what it's gonna be, like,
Like the exams are more.
It's going to be a little bit longer because, this is a 2-hour final, and I've got a lot of material. So it's going to be about equal weight on the 3 exams. So, other than the spectroscopy, NMR and IR, everything goes together. So it's really very good differentiation between the chapter and alcohols and the chapter of ketones and a carboxylic acid. There's no reaction all in there. But it's just like 2 exams or something like that.
oh, just like our last exam, like 8, questions were like 1 to 2, like group outcome.
Everything we covered this semester, plus anything from organic 1 that applies to here. There's going to be, problems just like this. The only thing is no mechanisms, but everything else just like your regular exams.
conjoint? And you said you're gonna put the extra on the exam first?
Yes, typically what I do is in the synthesis part at the end, let's say I give you 5 different syntheses, and I'll say, well, 3 or whatever number out of these are extra credit. So I'll typically, your best ones are gonna be for credit, and any additional points that are left are extra credit points.
Is it 10 extra credit points on it?
Probably.
We're still in our damage chart.
Yes, I give you that. So epoxides can be opened in one of 2 ways. Under acidic conditions or under basic conditions. If you're under acidic conditions, let's put some methanol so that it becomes like this. As usual, the acid is there to make this into a better electrophile so that your nucleophile, which is weak, can attack. Now, you can write this like this, but the fact of the matter is that you could also write this as sort of like, well, this is sucking electron away from these carbons, but it would be able to suck more electrons away from here because it's got a substituent that can help out. So this carbon is more positive. And so your nucleophile is going to selectively attack the more substituted carbon because it becomes effectively the more electrophilic, the one that can better bear most of the positive charge. And so this will open up like this. And after you use hydrogen, you will end up with that. Now, if you open that under basic conditions, then your strong nucleophile is going to go to where it's easier to approach. And where it's easier to approach is the least substituted carbon. It's more open, it's less sterically crowded. And so now, we don't have H+, this is an alkoxyl ion. And then we toss the wolfenium acid, we're going to end up with something like that. And so you can see that what's connected to the carbon with the methyl group is now, it's kind of the opposite. So the specific reaction that we had in here, rather than using an alkoxide ion, I was using a Grignard. But a Grignard is a basic type nucleophile, and so it's going to attack on this carbon as opposed to under acidic conditions, we're going to attack on this carbon. So that's where you end up with a different reach of chemistry.
Okay, so that one represents H2 doesn't have it off, and our bottom is the Grignard one.
So yeah, let's assume if this had been a Grignard, then this would have been a methyl group or something like that. So the problem is this is an acidic hydrogen. So rather than this attacking as you would expect to form this product, this base is going to attack this acidic hydrogen, form this alkyl ion, and then when you toss out an acid, go back to the starting material. So that is why you cannot use Grignards in the presence of an acidic hydrogen. I have a final tomorrow from 10:30 to 12:30. Before or after that, I'll be in my office. And obviously before the final on Thursday, I'll be in my office. So if you happen to have an additional question, you can either email me or you can come by and I can answer them. Other than that, overall exams, practice, maybe some of the fast problems if you have time for that. Definitely, the type of questions you have in exams is okay.